cells on the screen.
Yeah, but you should get our picture like out of the way, cause yeah. No, minimize it. There we go. So we're gonna start off today with a special topic lecture about task and motion planning. So the very fundamental topic in robotics, of which Hedja is an expert in. And then after that, I will have a few final exam questions that we can go over. So, and then if we don't get it through all of them today, we'll have more on Wednesday's class. So yeah, without further ado, let's get started with Hedja's presentation.
Okay, hello everyone. Today we will talk about task and motion planning, or TAMP. So it is a very interesting research topic, in my opinion. So at the beginning, I want to mention that there is a very good survey paper about TAMP. So if you are interested in this topic, you can try to find this paper and read it. And TAMP is proposed for solving long horizon manipulation tasks. And by long horizon manipulation tasks, I mean manipulation tasks that have multiple steps or multiple actions. So in the real world, clearly there are many manipulation tasks on long horizon. And here I can show you some videos where robots are performing long horizon manipulation tasks. So in this example, the robot is trying to move the green block to the stove and try to heat it and try to serve it on the plate. So we can see in this example, the robot needs to pick and place the green block several times, and also it needs to turn on the stove. So there are multiple actions. Right? And the next example is a table clearing task. So in this task, the target is to move all the objects on the table to the basket. And clearly there are also many actions. And yeah, let's finish this. Oh, I have played one. So in this example, the robot needs to move the colored boxes or colored objects into the corresponding colored boxes. So in this example task, there are multiple robots. So we also need to consider the collaboration between robots. And it's easy to see that all these manipulation tasks are long horizon, and we want to generate robot plans for performing these long horizon tasks with a single framework. As I said, TAMP is proposed for solving long horizon manipulation tasks, but we also want to ask, we can first ask whether we need TAMP to solve long horizon manipulation tasks. Can we solve long horizon manipulation tasks with some existing techniques such as motion planning or task planning? So here I will show you an example simple cooking problem. So it's a two-step manipulation problem. The target is to move the green block to the stove. So robot just need to do one pick action and one place action. Now we can ask, can we solve this example cooking problem with motion planning? Can we solve it with RT or PRM? Right? And in motion planning, we are given a start configuration and a go configuration and the kinematic information of the environment. So the kinematic information of the environment describes how objects how objects are related to each other and how what is the kinematic information of the robot. So how the links of the robot connect to each other. So the target is to find a collision-free sequence of configurations starting from the start configuration Q and ending at go configuration Q prime prime. So now actually, if I have an animation, I want to ask you whether we can solve the example two-step manipulation problem with motion planning. Can anyone tell me whether we can solve it with motion planning? Why or why not? Yeah.
If you do two separate into two motionless codes, like Q to Q double, Ram is going to be like, let's say, placing the green block on the stove, and then you just have another, you define your Q double dot to be like the power switch.
Right. So as you said, you want to first formulate one motion planning problem and then formulate another motion planning problem. Because the kinematic information changes after the peak action. So after peak action, the green block is no longer supported by the table, but it is firmly attached to the robot hand. So the kinematic information of the environment changes, which means the feasible configuration space of the robot changes. And that's why we cannot solve our two-step manipulation problem with by formulating a single motion planning problem. So we need formulate two motion planning problems. Okay, so here I have two figures. So the kinematic graph encodes the kinematic information of the environment or of the whole system. So the nodes of the kinematic graph represent the objects and the joints of the robot. And the edges of the graph denotes the attachment relationships between the objects or the relation between the joints or the robot links. So before the peak action, green block is supported by the table. So there is an edge between the green block and the table. And after the peak action, robot grasps the green block. So the green block is no longer attached to the table, but it's attached to the robot hand. So the kinematic graph changes after the peak action. And this means we cannot formulate a single motion planning problem to solve this two-step cooking problem. So we need some approach to handle this kind of kinematic graph changes. And this is where we need multimodal motion planning. So in multimodal motion planning, we attempt to find a sequence of collision-free robot configurations given a start configuration and a go configuration and a set of modes. So assume we already know that there are two modes. So each mode has a distinctive kinematic graph. Then we can use multimodal motion planning to solve this problem. Multimodal motion planning will try to sample robot configurations in different modes and try to connect configurations in different modes. Okay. So here I visualize an example path we can find by running multimodal motion planning to solve our two-step manipulation problem. So Q denotes the start configuration, and Q prime denotes the Q prime primes denotes the end configuration, and sigma denotes the kinematic graph before peak, and sigma prime denotes the kinematic graph after peak action, and F sigma denotes the feasible configuration space before peak. So we can see the feasible configuration space of the robot changes before peak actions. And the robot and the planner needs to find a path from one manifold to the other manifold. So now, can we solve our two-step manipulation problem with multimodal motion planning? Can anyone tell me? So
wait a little more.
right. So now actually we can use multimodal motion planning to solve our simple two-step manipulation problem. But in many complex manipulation tasks, there can be a lot of modes. And if we just run multimodal motion planning, we will have to sample robot configurations in each mode. And some sampling are actually not like unnecessary for a given specific target. So it can be very inefficient. And we want to actually find a sequence of modes that are relevant to our target specification. So if we want to move the grain block to the stove, we just want to sample robot configurations on the modes corresponding to kinematic graph that before the peak and after the peak. So we want to find that sequence of modes efficiently, and that's when we need task planning. So here, task planning is usually will be we will learn task planning in AI class. So PDL is a standard language for defining task planning tasks, and there are many task planners that can solve this kind of discrete task planning problems efficiently. So as long as we can discretize the world, and we can manually define the discrete states of the environment and also the discrete actions, once we define all this information, the task planner can efficiently find a sequence of discrete actions. So, and each discrete actions can correspond to a mode, and we can do motion planning. Okay. And now we can, as we can see, all these existing tools are useful for solving long horizon manipulation problems, but they cannot solve long horizon manipulation problems by themselves. So task and motion planning tries to integrate all these existing tools and try to solve the long horizon manipulation problems by combining them. And here we can have a definition of TEMP, which is TEMP is the extension of multimodal motion planning, leveraging the power of task planning. And here I also show, because we have a standard language to define task planning problems. So if we want a similar standard language to define TEMP problem, we will see that when we define the actions for TEMP problem, we, instead of, besides the discrete arguments like which object to pick, so for pick action, we do not only need to decide which object to pick, but also where the object is located, and also what grasp pose to use to pick the object. So for TEMP problem, we do not only need to search for discrete action sequence, but also the continuous parameters.
I think we should pause for a question if anyone has any. I get no question.
So there is a variety of planners for TEMP, and because TEMP is a very hard problem, so most planners are just focused on some certain aspects of the problem and try to solve it effectively. And we can also categorize these planners by whether they first search for continuous parameters or they first search for the discrete action sequences. So there are methods that first search for continuous parameters, then search for discrete action sequences. And also there are methods that first search for action sequences, then search for continuous parameters. And also there are methods that stand in the middle. So we can first, I will first introduce a method that first search for continuous parameters and search for action sequences. Because of the time limit, so we cannot go to detail for this method, but I will just briefly talk about this. So PDL stream is a well-known method for temp, and the PDL stream first samples, it has a pre-processing phase, and in this pre-processing phase, it will try to sample a set of values for continuous parameter domains. So once it has a set of continuous parameter values, actually we can formulate the whole planning problem as a huge discrete search problem, and we can solve it with the state-of-the-art task planning techniques. Like we can just use some existing task planning techniques to solve it. And we can, here I will show you some example demonstrations of PDL stream.
Is there actual water in that cup?
No. Okay, so now we can also, now I will introduce a method that first search for action sequences, then search for continuous parameters. And as we can see in the PDO stream, the target is specified as some symbolic task specification. So the target is like place a green block on the stove or place a cup on the plate, right? But sometimes we also care about the final geometric state of the environment. So in this, in logic geometric programming or LGP, it attempts to solve this kind of problems. So where the objective is given in terms of a cost function over the final geometric state. So this is one example problem. So the initial state is like there are a lot of objects on the table, and the target is to build a tower with these objects as high as possible. So clearly we cannot solve this problem with PDO string, but we can, so LGP is, LGP tries to solve this problem. So in LGP, it will first sample a discrete action sequence. So for example, in this example task, it can be a sequence of pick and stack different objects. And once we know what objects we will manipulate, it will try to optimize over the space of the end configurations of the whole system. So it will find, for example, this kind of end configuration of the whole system. And then it tries to optimize jointly over all switch configurations. So if we only consider pick and place actions, the switch configurations will be the pick and the place configurations. And finally, it can optimize over the full path. So here we show you some demonstrations that of LGP, and I find LGP is very, like, the demo of LGP is very impressive, as it shows how to intelligently use tools and to like do some complex manipulation tasks, like comparing with just pick and place actions. So here the task is to use it can use the wall to move the ball, and this solution is to kick the ball from the behind and grasp. So all the here the target of the robot is to grasp the ball that is far away from it. But we can find like LGB can find a lot of different solutions to do this and to utilize different objects in the environment. So now we can, there are also some methods that stand in the middle, like it don't directly find an action sequence, but it incrementally it incrementally gets the action sequence. So okay, so the method I will introduce in the following slides focuses on a subclass of temp, which is called geometric test and motion planning. So geometric test and motion planning focuses on the geometric aspects of the temp. So here are some example geometric test and motion planning problems. So on the left, it's a task where the robot tries to move the boxes from one room to the other room. And there are some movable obstacles. So the robot needs to figure out which obstacles should be moved out of the way such that it can perform the task. So this is a video. Okay, so also packaging task is similar. There are movable obstacles, and the robot needs to manipulate. The robot needs to move the target objects into target regions among movable obstacles. So in the paper I want to introduce, we extend geometric test and motion planning to multi-robot domains because multi-robot systems can perform some actions that, such as handover actions, to increase the efficiency of the overall task execution, and it can also, like the different robots can also concurrently manipulate different objects, so to increase the overall task efficiency. So this is one example to the multi-robot G10 task. And the target is to move object M1 to region RE1. And we have 2 robots and 5 objects. And to solve this task, we have a 2-phase framework. So in the first phase, we want to compute collaborative manipulation information related to the task, because we want to generate some intelligent collaborations strategies between robots. So we want to know that which robot is good at doing like what actions. For example, if for robot R1, it can pick up object M1 without colliding any objects, then it's better to ask robot R1 to pick up object M1 instead of ask robot R2 to pick up robot object M1, because object M3 will be a blocking obstacle. So once we compute this collaborative manipulation information, we will first do optimization-based task skeleton generating. We will have initial task skeletons. So the task skeletons can be thought as some task plans or sequence of actions. And we use it to initialize a search tree for the whole for the task and motion plans. And in each search iteration for this search tree, we will select a promising task skeleton or the sequence of actions, and we try to ground it, which means we try to instantiate the continuous parameters for this task skeleton. And if we failed during grounding, we will try to use task skeleton generating to generate more actions to fix the conflicts emerge during grounding. And this search will continue until we find a successful task and motion plan. So, so this is an example demonstration showing 4 robots performing the G10 task.
Are you supposed to drop the thing in the bin or just put it on the edge? Or is the thing you're not supposed to actually put it on the bin?
So I disabled the dynamics in the simulation, just only kinematics. Yeah, okay. So this concludes my presentation. I'm happy to take any questions.
I thought you were going to talk about our GPT work. Or maybe we'll talk about that in the next year.
Next year. Okay. Yeah.
Question.
So for the task planning, we assume we have a central planner for the whole system. Then we will just generate plans that include action for all the robots. Right.
For example, we have 2 robots, A and B.
Yeah.
So we can pick up the same block. But then how do you determine how to collaborate?
Right. So because we first compute manipulation information for individual robots. Right? So for example, for 2 robots, they can both pick up object 1. But there we can compute like the distance like between the robot and the object, or we can compute the distance in the configuration space, like from the robot configuration, initial configuration to the peak configuration, and we can use that as some evaluation metric. Like we can use that in the cost function, and to do an optimization.
The robot 1 picks up first block and the robot 2 picks this block.
Right.
How are we determining the robots don't collide?
So in my work, we assume robots synchronously start and stop execution. So I will check collisions between robots at the peak configuration.
We find out the overlapping waypoint.
Yeah. How about just assume that the robot 1 are trying to move the block right here, and when you just look at it, the arm may move without an obstacle, like the movement of a certain robot arm may change the environment of it. So how can you assure that each of the movement can individually be separated instead of interfering with each other? Each movement will. What you mean how can you?
Just go back to the slide. The second It's like a easy one.
Okay.
Okay. Just assume like the left one is trying to use the green block right here. But with this moving, it's highly possible that it just may move out of the white blocks, right?
It will what? It will collide with other.
It will collapse with the white blocks.
Yeah.
And the white blocks may possibly just on the path, like the second, the right mechanical arm is movement. So the first last movement may totally change the action dynamic of the second one.
So when we do motion planning, robot will try to find a collision-free path. If this robot tries to pick up this green block, then it will avoid hitting other blocks, other objects.
But right now we assume that the whole environment is stable, and we'll just move effectively or we'll just do something else.
Yeah, if in this demo we assume the objects can only be moved by robots. So if it's for example, there are other like humans that accidentally moves the objects a bit, then the whole plan will be invalidated. So one way to do that, one way to overcome that is to like do a replan.
Maybe last question. Can you discuss what you're going to do with future work? What are you going to do this summer?
Yeah, so there are many right. I've got the one slide for future possible research directions. So I think nowadays, like in general, I think more and more works are trying to combining learning with planning, because we can see in all the planners, if we just do a pure planning approach, we for each new problem instances we need to plan from scratch, and it can usually be very slow and inefficient. So there are many works try to combine learning into planning framework, so they can learn from their planning experience for more. And also, I think when we are dealing with and also for task planning, a task and motion planning, as we have mentioned, the importance of task planning, but it's actually hard to manually define the planning domain. So nowadays, a lot of people try to use large language models for task level planning. So probably it also presents an opportunity for extend temp to open environment where there are a lot of objects, and humans cannot predefine all the possible objects or all the possible actions. So there are many interesting future directions can be done here. And also, I think when we consider more dynamic environments, we also need to consider like how these task and motion planning agents can collaborate with humans, where they do not only need to perform tasks, but also they need to consider human preferences and also predict human intentions and try to account for the uncertainties of human intentions and preferences in their planning framework. There are still a lot of works can be done in this.
I think that's good.
Yeah.
We're working on that this summer.
Yeah, I'm trying. Yeah.
I think that's it for the TAMP part. So let's thank our speaker again. take a 5-minute break and then we'll get to the next part of the class. And Chuck, you can turn off your camera.
Okay.
Or log out of Zoom to that.
Yeah.
Try to figure in artifacts in the image. I guess that would be a typo. strange here. What is this, by the way? What is that? All right. So maybe I think we should probably get started. Um, yeah, so anyway, welcome everyone to lecture 27, although we're halfway through it, but no. The first half was the special topics. So what the TA, he just left, but what he was just presenting was an example of what people are working on in the research community. So I thought it would be pretty interesting to talk about. So going forward, we're now going to talk more about the logistics and then the final exam. Since we're already at the very last week, we only have 28 lectures in the class. So some logistics and then also other things. So yeah, lab 4 and homework 4 are due at the end of this week. So hope that's going pretty well. Your final exam should be on May 1st. So unfortunately or fortunately, depend on your view, but I think the final exam period is May 1st to 8th. So we got assigned the first day, which is good or bad depending on how you feel about it. I honestly don't know. For me, it's good because I have to leave for a robotics conference on May 10th. So I'm hoping we can finish the exam, then grading, then potentially regrade requests, and then the final grade before May 10th. So I'm working on making sure I understand all the logistics. So I think the final exam is in this room. I'm not totally sure. Do most final exams happen in the same room for the normal lecture? Because I was not told where it is. So I'm trying to find more information. I'm gonna assume it's over here, which there's enough space, I think, from the midterm, like everyone had one free slot to them, either side, I think. At least one free desk next to them. If there's more people, then maybe we can use this table or something else to help separate people. All right, and because it's the last week of lecture, I'll have an extra office hour Thursday this week from 1 to 2 in my office. So we can talk about the exam, or we can talk about homework 4. And I'll also have my normal office hour today after class. And the policy for the final exam are pretty similar. So you have your 2 cheat sheets instead of 1. So you hopefully keep the one from midterm, or if you threw it away, then make a new one. And then, yeah, topics to cover. It will cover the entire course, though. Like basically, unless I said it's not going to cover something here, we could cover it. So it could cover anything in the course, but most of it will be on the second half. But I can't give like a percentage because it's ambiguous. Like sometimes some concepts are really part of like multiple lectures, so it's pretty tricky to give a raw number. But I can say I'm currently 87% done with the final exam. So I just need to make 13% more of it and then test it on the TAs, and then we're good to go. Any questions? I mean, for the midterm, I had tons of questions about the format, but it's going to be similar to the midterm, except more emphasis on the second half of the course. So, all right. So maybe we can get started with some practice questions to try to reinforce some of the things that we talked about earlier. All right, so let's talk about value iteration, because I feel like a lot of people had questions about how did value iteration work. So let's start by considering this grid world. So let's go through it slowly. We have a discrete grid world Markov decision process. So it's kind of like we had that agent, and then it could move up, down, left, and right. And then in certain states, there was a special exit action. So what we have here is something similar. It's 3 rows, 4 columns. So there's, each of these that's not shaded is a valid location where the agent could go to. So if the agent or robot is at A, then if it goes up, it's just going to stay where it is because that obstacle blocks it. Same thing if it goes down. If it goes down, it's going to stay at the same spot. But it could move left or it could move right. But the main difference with what we had talked about in class is that when the agent is in those two states, the upper right and lower right, it can do the normal, up, down, left, and right, but it has a fifth action, a special exit action. So if it takes an exit action, it lands in the T state. And you know what T, you can probably guess what T means, right? Terminal. So that means it's done. So once the agent is stuck there, once the agent goes there, then the episode is basically over. Now so it's very important to know whether you're getting a reward when you enter or leave something. So to make it very clear, we get the reward upon taking the exit action. So that means if the agent is in the is in this cell, then it can go right, but it gets no reward. So there's no other reward. But once it's there, it can take the exit action. It goes to T, it gets +1 reward. And then the episode is over. All right, all other transitions other than the +1 and the +100, they get no rewards, so 0. The MDP is deterministic. So if the agent goes up, it goes up with 100% probability. Of course, it might be blocked, but that's not the point here. The point is whether if it intends to go up, will it actually, execute, the action going up. So any questions about the setup here, like the assumption? So here's one question. If your discount factor is 1/2, and you run value iteration starting from all the states as 0. So I guess, you do I guess to make it more formal, I should have written like B0 equals 0. Yeah, so really we should have the subscript, but then what are the optimal values of A and B at the end after a value iteration conversion? So think about that for a bit, and then we'll go over the details. Everyone can see this from back. How's it going? Are you in the middle of computing it, or just give up and want me to explain it? Or you might be giving something like this on the exam. That's why we're doing the final exam review. I mean, obviously not this exact question. That would be a bit strange. So. Oh yeah, question?
I was just gonna, are we like giving it a test?
Yeah, yeah. Do you want what do you think?
Like for B star, would it be take a step and then you take another step, so it's gonna be discounted by 1/2 squared of 100, so like 25.
Oh, what is 25? A or B?
Like a quarter of 100 of the rule.
Yeah, but wait. So you're saying B star A is 25. What is B star B?
Well, however many number of steps.
What are how many number of steps?
Okay, 100 divided by 64 would be B star B.
So let's go over this. So I think, oops, sorry. So B star A is 25. That's good. B star B is 25 over 8. So 100 over 32. So let's go through it. So the way to think about this is you can try running value iteration and computing everything, but an easier way is just to think about, all right, what is the optimal thing that you could do from A or B? Because that's what value iteration is going to give you. It's going to give you the optimal value from a given state after you run it infinitely often. Although, as you'll see, you don't actually have to run this infinitely often. So from A, you're in A. So it seems like the best thing to do from A is to go straight right as an exit. So the agent is in A. It goes here. The reward that it gets is gamma 0 times 0. If it goes here, the reward that it gets is like gamma 1 0 because there's a discount. Now it goes here to the exit, gamma squared 100, but gamma is 1/2, so it's 1 over 4. Then 100 divided by 4, 25. Right? Now, the more interesting thing is what happened at B, right? Because does it make sense for B, do you go just right and then exit? Or do you go right down, and then exit there? That's the interesting question. So the way to think about it is, if the agent is over here, it can get +1 reward. But let's suppose it goes down, and then exit. It gets 0 with discount, it's 1. It gets 0 with discount 1/2. Then it gets +100 with discount 1/4, which is 25. 25 is better than 1. So it's going to be better to go to the exit. So the way to do it is, and also because it's a grid world, you can go like 1, 2, 3, 4, 5, 6, or you can go down like 1, 2, 3, 4, 5, 6. Like as long as it gets there within like 6, actions, it's going to be fine. So, I mean, if you want to do it mathematically, like this, think of this as gamma 0, gamma 1, gamma 2, 3, 4. This is gamma 5, and then 1/2 to the 5th power 2 to the 5th is like 32, right? Like 2 to the 4th is 16, 2 to the 3rd is 8. And then it's 100 divided by 32. Whew. Any questions about that? All right. After how many iteration k will we have bk of f equal the optimal value for all the states? So it's a little bit trickier here. So assuming you have a discount factor of 1/2, after how many iterations, the value iteration, do all the numbers like converge, and then you don't have to do any more iterations of value iteration? Going well? 'Yeah, so for a question like that, like I recommend the way I would do it is just have like a paper, then insert like what the value would be, and then I feel like from there the answer will kind of pop out after you do it in some number of iterations. So, yeah, I'll give you a few more minutes to think about it. Like, what do you think? 2, 3, 8, 42? What's an unlucky number in 13, 13. Yes. What about other countries? What's an unlucky number? I don't know. Alright. Well, maybe let's just go through it now. Then uh, so Hi, so the answer is 6. So if you got that, then congratulations. So let's discuss why this is the case. So when you start value iteration, everything is 0. So everything is 0 when you start. Now, let's suppose that you have one time step left. So there's only one, like, one iteration left. That means the only state where we get any reward are from these two. Because with one time step left, this one takes the exit action, immediately gets plus 100. This one takes an exit, immediately gets 1. So let's mark that in. But I also wrote there that this one, you can probably guess is going to be overridden at some point. Because value iteration, you take the max over the possible choices. So you can go here, but you can also go down and then get the plus 100. But we don't know that yet because we've only done one iteration, and that requires 1, 2, 3 action to get there. After 2 iterations of value iteration, we get we get 50, 50, and 1/2 here. Because the discount factor is 1/2. So if there's 2 time steps left and you're here, you can go 1 and then exit. So you get 0 plus discount times 100. That's 50. Now this is 50. You could have gone up and then exit. That would be 1/2. But because 50 is better to go down and then exit, you exit. So this is after 2 iterations. Now let's do a 3rd iteration. This is 25. This is 25. This is 1/4. But then what's over here? Like with 3 time steps left, now we know from value iteration that we could have gone down 1, down twice, and then exit as our 3rd action. So now that's 25. But we still have to do more iteration because like these still need to be updated. So now, so after 4 iterations, let's write down the iteration numbers. Like after 4, we now get 25 over 2. This is overridden. So 25 over 2, this turns to 180. But of course, this is going to be overridden later. So this should be what it's like after 4 iterations. And just so you know, like the reason why we don't update like 50 or 100 or 50 is because we already know that the optimal action, you don't even need 4 time steps. You just, if you're here, you just exit. So you immediately get 100. There's no other better option. Well, that's why this doesn't get updated after more iterations of value iteration. All right, now after 5, this goes to 25 over 4. This is 25 over 4. That's 1 over 16. So this is after 5. So do we have to run one more? Because this is 1 over 16, and we already said it should be 25 over 8. So after 6, all of these are the same except this is 25/8, which is what the optimal value of B is. So after 6th iteration, we arrive at the final value. Question? All right, so suppose we change the reward function to be the reward at every single state action next state tuple is -1. So we change it, so there's no more like +1, there's no more +100, everything is -1. Any state action next state is -1. So does that change the optimal policy? So this is asking about the optimal policy. It's not asking about the values. Like the values will change because we're changing the numbers, but is the policy going to change? That's what we're asking here. So think about that. Anyone? I mean, it's a binary choice. I mean, if you say something, you have a 50% chance of getting it right. Although on the final exam, we'll probably give credit mainly if you give a justification with it. So, you know. Yeah, so does the optimal policy computed from VI change? Remember that a policy here means every single state, the policy should specify where the agent should go. Yeah. Why?
Yeah, E is 5 away from the word of 100. So that means if we take 5 time steps, then we're going to have -5 added to the reward. And in this case, since our reward is 25/8, we would have a negative reward compared to if we take like 1, 2, 3 time steps to the other reward.
So I think what you're saying is okay, but you're making it unnecessarily complicated. The only thing you have to here's what I would recommend. I would recommend comparing what happens here. So if you're in this state under the old reward of +1 and +100, the optimal policy is to go from here, go down, and then exit. That's what the optimal policy will tell you. But if you change it to be reward to be -1 everywhere, then the optimal policy will tell you if you're here to exit instead of going down and then exiting, because every reward is -1. The agent wants to leave as early as possible. So you can compare other states, but I think the easiest one conceptually is like this one, because you can exit right away. Then otherwise, with the older reward system, it's better to go down and then exit. Yeah, so the optimal policy will change, then the agent now exits as soon as possible. Yeah.
I'm curious about within question 3, still the discount factor that we have to right now.
Well, the discount. Oh, the discount factor. Well, I should have clarified assume the discount factor is the same, like 1/2.
So
I should have clarified it. Depending on if the discount factor, like you might get some different policy. In general, you will get a different policy if you change the discount factor. But I should have clarified to keep the 1/2 assumption.
yeah, as first of all, if we just keep discount factor as 1/2, and maybe the best policy for the top right corner shouldn't be exist. It should go down and go down because
Which under which reward system?
question 3.
Oh, you mean if it's all -1?
Yeah.
No, because if it this is saying you get -1 reward for every action. So if you're here, you get -1 from exiting, and then you get -1 total. If you go down, you're getting -1, -1, -1. So no matter what your discount is, you're gonna get something worse than -1.
So there's no +1 for true reward in that.
Oh, yeah, I should have, yeah, it's for all.
Okay.
On the exam, we'll try to make it clear that, no. I had limited space to write out everything here, so it really should have been, yeah, -1 for every single date action next date, which include that exit action. Yeah, I'll probably make an edit to the slide. All right, that was good. All right, how are you feeling? So you see that the number is 1A, right? What do you think is going to happen next? All right, so we're going to have more final exam review next class. So the exam is not entirely about value iteration. I just feel like it's a question that we haven't had a chance to do in the homework, so we'll do it here. All right, so now we have a different MDP. So we have the same assumption as before. It's like the same, same action phase. You get the 2 exits, but now we have a third state where we can exit. So here we can take an exit action with reward plus X. So if you're here, you have the 5th action, which gives a reward of plus X. For what value of X is it guaranteed that our optimal policy tells you that if the agent is at state C, you should go left? It might be in a certain range, like you might have X is greater than something, less than something, so think about that. Oh yeah, question? Or do you have the answer already? Yeah, what? X is greater than or equal to 50. So the I would have accepted X is greater than or equal to 50 or X is greater than 50. You can argue that if X is equal to 50, it's indifferent to 2 things, or you're not guaranteed to go left. Like you could equally go 2 to go right, but we'll be lenient, and then x is greater than or equal to 50 is okay. You see why that's the case? So because what happens is if you go left, then you're starting from C, you're taking, if one action, the second action, the third action, and then you exit. So the first time step, the discount, the factor is gamma 0, then it's gamma 1, then it's gamma 2, then it's gamma 3. So you get 1/2 to the third power. And if you remember from last time, you had 25/4 as the value for C. So you just have to make sure that this condition holds. Right? Any question about that? For what? Yeah, this might be tricky. So for what value of x does value iteration take the minimum number of iterations to converge to the optimal set of the optimal value for all the states? So we assume that we have gamma is 1/2. Yeah, question? Yeah, this one.
Yes. So the go back the previous slide with the value of the column before. So for like, how do you get 25/4?
Oh, so I had it written over here, but this is 25/4. That's the number that you get from value iteration. So it's like you get 100, 50, 50. Yeah. So if the discount is 1/2, then this is the value at this state if we choose to go right.
If I take consider this slide for my mistake.
So think about that. Think about that. I'll give you a few more minutes to think about it. Does anyone have a, so what? 2 and 50? So do you mean x equal 2 or x equals 50? It, yeah, part of it. Yeah. All right, so x, all right, so the answer is 50. All right, so the values of x, it would be x is within 50 and 200. That will result in value iteration converging to the minimum number of iterations, which is 5 instead of 6. So, so if you notice what happens, if you've seen the logic about how value iteration works, then C and these two states, they're the ones that take the longest to update. And so what we want to do is make sure that like when we update one, it doesn't get overridden at the next iteration of value iteration. So there are different ways of trying to solve it. So the way that I did it was to try to do I put in a bunch of max terms. So I wrote down here's what I did. So I basically wrote down like max on 1, 4 after 5, so this is what I wrote after 5 iterations. So after 5 iterations, there was, we had x here, we had x over 2, then we had x over 4, then x over 8. So this is after 1, after 2, after 3, after 4, then there's another one here, but this one, by then the discount is so, it makes it very small. And then going from here, there was 100, then 50, then 25, then 25 over 2, and then 25 over 4. And this 1/8 came from the +1, not the +100, because you can go from 1 to, you can go from here to there within 5 actions. So this is what we had after 5, after 5 value iterations. So the purpose is to try to make sure we don't do any more changes after this. So after 5 value iterations, if this is like, if this is 25/4 and this is greater than like, x, we can keep going and updating by propagating x/16 and whatever, but it's not gonna matter because like, if 25/4 is greater than x/8, then this is already set. And so this is where we get the x is less than or equal to, oh, actually, sorry, this is actually, no, I think it's, yeah, so I think the easier, yeah, so I think the easier way to look at, those two components in the top right, and then check that and to check that they don't change. So I think the way I did it was like, if you think of x as 50, then this would be 50 divided by 8, which is the same as 25/4, right? And then if you have x as 200, oh, then you can compare with, if x is greater than 200, then this thing would be updated with I think this thing would be updated with the updated value of x. So I think if you had, over 16 versus 25/2, then, x versus 25. So what we have here is x/16, right? x/16. And then we want this condition to hold. And then, well, this condition results in x has to be less than or equal to 200. Yeah. Sorry for the confusion. So we just want to make sure that this doesn't get updated. And then I think what we wanted to make sure that, that this thing stays at x/4, although, wait, this is like 1, 2, 3, 4, 5. Yeah, then if you have x is, yeah, if you have x is, so if x is less than 50, oh yeah, well,
Yeah, I think, so if x is less than 50, the cell that's above the shaded one will get overridden, right? Looks like x/8 is, needs to be greater than 25/4.
yeah. Yeah, I mean, this is, I think, yeah, I think this is roughly what I did when I was trying to think about this. So yeah. Oh yeah, so I think what we wanted to, yeah, you actually, wait, like 1, 2, 1. Oh, so I think the minimum number of value iteration depth, I think is 4 here. You might, 1, 2, you might be able to, Yeah, you might be able to get it done with 4. All right, so this all right, I have to fix this because this is yeah, I put in an extra date in my notes, so yeah, I'll fix this thing here. Yeah, yeah, yeah.
You say like value iteration number, that's like including 0. So like taking one step and another one, that's like a value of 1. Or sorry, wait, maybe 2.
Yeah. Well, I think the B0 is what happens when everything is set at 0. And then like B1, like if you have one iteration of value iteration, we get a 100 here, and a 1 here, and then X here. So that's like one iteration. And then after the second, you would get this. After the third, you get this. After the fourth, you get this.
Okay, so one iteration is B2.
Yeah. Yeah. All right, we only have 10 minutes left, but I'm going to say, so we went through one question, which is one question of value iteration. And all right, this is the last question, and then we'll continue with the practice question next class. So reinforcement learning and Q learning. So if you consider the following MDP with 3 states and 2 actions, you're given the following interaction sample in the table here. So you have state, action, next state, and the reward we get during that state, action, next state thing. So there's 6 interaction data points. So it's kind of like you have the agent ran in the environment, you have 6 data points. So run Q learning, the online Q learning on these samples. And then assume that the discount is 1 to make the math simpler, and that alpha is 0.5. And what does the Q learning give for these two? Yeah. Yeah, so after looking at this again, I think you had 4 iterations of value iteration, because this is after 5, and then in order to avoid a 5th one, you have to make sure that 25 over, like x over 8 is greater than 25 over 4. So that would be x is greater than 50. Yeah, that makes sense. So I just want to make sure you have 4 iterations, which is the minimum number before conversion. Yeah. Yeah. All right. All right, 6 minutes left. I'm just All right, so I'm gonna do Q learning on the first sample here. So do you see what happened though after the first iteration of Q learning? All right, we're gonna go through in order, so like row by row, right? So the first row is updating state of A and the action of go, which by definition is 1 minus alpha of the current value, but we assume everything is 0 to start, plus 1/2, which is this term, so it's 1/2, and then you have 2 reward plus gamma times the max over all the Q value, but we have nothing here. Everything is 0, so this is 0. But you still have 1/2 times 2, which is 1. And so after the first iteration, you get A of go is 1. That's the first iteration. Now the second iteration of C stops. So it's the same thing. It's multiplied by the current Q value, which is nothing. So it's 1 minus 1/2 times 0, so it goes away. Plus 1/2. Oh, the reward is 0. So okay. All right. So it's 0 plus 1. This is the gamma times the max of all the actions to a time of. So A is the next state. So we have 0 instantaneous reward, but it's plus 1 times the max over all possible action at A, because A is the next state. But we know that the max is 1 because we just computed a 1 here. So this thing is 1. And then you get 1/2 times 1, which is 1/2. So this is 1/2. And then, so because of time limits, I'm gonna go through the last one. I'm gonna go through that a little bit more slowly next class, but the idea is that after we've done Q of C and stop, then we have no other data point to update the Q value of being in state C and taking action stop. And so when we make this 1/2, like that's it. We already know that it's 1/2 and we're not updating it anymore. All right, any questions about that? And I'll go through this again at the start of next class. So hopefully that was a little bit clear. Like when you do the Q learning, you initialize all the Q value that something like 0 if 0 is a good option, and then you go sample by sample, update based on that formula. The tricky part is really understanding, like I think this part is really tricky. Like when the successor state is something you have to check if it's like you have to check the successor state and then all the possible actions. All right, so I think I'll see you on Wednesday for the last class, and then hopefully by then I'll know like where the exam taking place. So all right, see you Wednesday.